Here we can see some distortion that can occur with cylindrical projections. The red areas are high areas of distortion with the yellow medium and the green low. So we could see that the low levels of distortions are at the prime meridian, one standard parallel, and then we have the the secant, the two standard parallel cylindrical projection, and then of course at the poles you have the higher distortion. So these images show that the popular Mercator projection distorts area and distance everywhere but near the equator. Here we have distortion along the parallels and meridians, in area, and in form. Mercator preserves the form of the areas but greatly exaggerates distance and area. Note the size of Greenland and Africa over here. Greenland is 0.8 million square miles and Africa is 11.6 million square miles in reality. And here we could see them looking as if Greenland is almost larger than Africa. If you check out Antarctica down here, it's way bigger than all of the other continents put together, and that's just not true in any way. Okay, so conic projections are good for mid-latitude regions such as North America or the continental US. So let's look at a couple of examples of conic projections. So we have the Lambert conformal conic, which was published by Johann Heinrich Lambert in 1772. The Lambert conformal conic projection preserves shape using two standard parallels. Parallels appear as curved arcs closer together near the center of the map. Meridians are equally spaced and cross parallels at right angles, preserving shape. This projection is well suited for mid-latitude regions or countries with an east-west orientation. The Albers equal area conic was published by Heinrich Christian Albers in 1805. The Albers equal area conic projection is another normal aspect conic projection and one that is frequently used in equal area projections for the continuous US. Similar in composition and appearance to the Lambert conformal conic, parallels are laid out as a series of concentric arcs, and meridians are equally spaced and cross parallels at right angles. So again, if we look at conic distortion, the red is high distortion, where low is green. And so we can see, depending on whether the conic projection is tangent or secant, we have different variations of distortion. So Albers is a conic projection that is used to represent regions in the mid-latitudes, including the United States of America. And we can notice over here that regions below the equator are highly distorted, with the South Pole being stretched into a huge circle around the outside of the map. And the North Pole is also distorted and is made into a circle, even though it is really a point. This shows that while Albers maintains area, it does so at the cost of distance distortion. Okay, so azimuthal projection or planar projection methods project geographic data onto a plane. They are typically used to represent data at the poles. They can be tangent or secant, and then polar, equatorial, or oblique. The orthographic projection is a special azimuthal projection that makes it look like we are looking at the Earth in a photograph. Google Earth uses this projection. Take a minute and examine the graphic and think about where the distortion is high and where it is low. Okay, so again, here we have an example of planar distortion. And so depending on whether it is tangent or secant, you're going to have less distortion at the poles, and then it radiates out, and then you'll see here, at the pole there's some distortion, where then around the pole it's okay, and then it gets worse on the way out there. So there's a few different things that you want to consider when you're choosing which projection you're going to use. And, nobody's expecting you to know all the projections. Most of the time we'll be working in the same projections over and over again, and we'll get that, we'll get into that later with spatial reference systems. But again, the considerations are, what's your goal? You want to have minimal distortion, and for analysis in GIS, all maps must have a common reference. So you need to state what that spatial reference is, and then any layers that you're using are all going to be in that spatial reference. Okay. Also, when we're looking at projection names, usually it goes with the last name of the creator, what properties, and what type of projection. So you'll see Lambert, which was the creator, we talked about it, and then a conformal conic. And the same thing, Berman, equal area, cylindrical. So you can have a lot of fun with projections. Some people just like pushing the envelope, and so basically any mathematical equation that you could put into the GIS that lays that sphere onto a planar surface or on a 2D surface, you can project the Earth in whichever way. So let's go over a few different projections just for fun. So here we have the Schoening projection. So Wilhelm Schoening, he created this projection in 1882, and it's a conic projection. So Schoening set the standard parallels to 90 degrees north and 18.6 degrees south in order to create a map designed for the whole world, which is a rare case among the conic projections. Here we have Good interrupted Homolocene. So Good's Homolocene map projection is designed to minimize distortion for the entire world. It is an interrupted pseudo-cylindrical equal area projection. And it was developed by John Paul Good in 1925. Here we have the Bartholomew Regional. This is an equidistant conic projection, and it's used for latitudes above the Tropic of Cancer, which is 22.5 degrees north. And here we have a lotus projection. So this is actually a variation of the Bartholomew. So John Bartholomew's World Oceanography Map is using a custom lotus projection here. Its southern part is a conic projection. The top three lobes use the bone projection. The faces connect perfectly when the two projection types represent their common parallel as the same portion of a circle. So, as we were looking at the Mercator projection earlier in the lecture, there's a lot of issues that come up now with teaching our youth with the Mercator or Robinson. Any map projection that is distorting the size and shape of the countries can be viewed as political gain. And so though the Mercator projection is really great for navigation, it's not really the best representation of the Earth when we're talking about, where things are and what they look like. So the Waterman projection here shows the equator clearly, as well as continental shapes, distances within 10%, areas within 10%, and angular distortions within 20 degrees, and relative positions as a compromise. Statistically better than all other world maps. So no other projection systems have been able to handle the management of those characteristics collectively as well. So pretty precise representation of the land masses on the surface of the Earth. So here we have a Cahill-Keyes projection. Cahill was the inventor of the butterfly map, which is comprised of 8 symmetrical triangular lobes. The basic geometry of Cahill's process for unfolding a globe into 8 symmetrical octants and producing a butterfly map. The octants were arrayed 4 above and 4 below the equator. As you can see in the slide, the octant starting point and longitude was strategically selected so all continents would be uninterrupted on the 2D map surface. This type of projection offered a 2-dimensional world map with much better fidelity to the globe than a Mercator projection. So here we have a bone projection. It's a pseudo-conical equal area map projection. The bone projection maintains accurate shapes of the areas along the central meridian and standard parallel, but progressively distorts away from those regions. Thus, it best maps T-shaped regions, and it has been used extensively for maps in Europe and Asia. And of course, it's shaped like a heart, so that's nice. So that wraps up the first part of this lecture. The spatial reference system video will be uploaded on Thursday at 6 p.m. So be ready for that, and make sure to wrap up the first week 4 of module 3, and jump into week 5.